spaces. Now, the theorem states that let Xt be a first countable space, then Xt is Hausdorff if and only if every convergence sequence in X has a unique limit point. Let us prove this theorem. Let Xt be a Hausdorff space. We shall prove that every convergence sequence in X has a unique limit. So we take a sequence, let Xn be a convergent sequence in X. If possible, let Xn converges to distinct points. And we have to prove this converges to a unique point. So suppose point X and Y be limits of this sequence. Let Xt, as Xt is Hausdorff, so there is two disjoint open sets G and H in X such that X belongs to G, Y belongs to H. As Xn converges to X, so by the definition of convergence of a sequence in the particular space, there exists some natural number n naught in N such that Xn belongs to G for all n greater than or equal to n naught. We know that if sequence Xn converges to some point X, then every open set containing X contains infinitely many points of the sequence except finite. So we have here taken some point n naught such that Xn belongs to G for all n greater than or equal to n naught. As Xn converges to Y also, so there exists some natural number m naught in N such that Xn belongs to H for all n greater than or equal to n naught. So let m is maximum of n naught and m naught. Then you observe that Xn belongs to G intersection H for all n greater than or equal to n this n. Because here we have this and for all n greater than or equal to n naught Xn belongs to G. So if we take m is greater than or equal to n naught, then Xn belongs to G for all n greater than or equal to n. And similarly Xn belongs to H for all n greater than or equal to n. So but here what we get, Xn belongs to G intersection H for all n greater than or equal to m means we get infinitely many terms of the sequence in the intersection, but we have assumed that G intersection H is empty, and so our assumption is wrong and the sequence Xn converges to a unique limit. Now, here we observe that in this first part we have not used first countability of the space. We have only used the space as Hausdorff space. But here in the second part we see that if the space is not first countable, then it is not possible to say that sequence converges to a unique limit. So conversely, let Xt be a first countable space such that every convergent sequence in X converges to a unique limit. We have to prove that space is Hausdorff. So if possible, suppose space Xt is not Hausdorff, then there are two distinct points X and Y such that every open set containing X has a non-empty intersection with every open set containing Y. Why? Why we have this condition? Because if space is Hausdorff, then for every pair of distinct points X and Y, we can get an open set, or we can say we can get a neighborhood which contains X, and we can get a neighborhood which contains Y, and neighborhoods are disjoint. But if the space is not Hausdorff, then we can get at least two distinct points X and Y, such that every neighborhood of X intersects with every neighborhood of Y, because the space is not Hausdorff. As Xt is first countable, so there exists monotonically decreasing local basis at X and Y. We have proved this result earlier. So let B of X be the collection of basis element, that is B and X for every n in n, and B of Y for the point y. It contains Vn of y for every n belongs to n. Here, as this is monotonically decreasing, so we know that V1x contains V2x, V2x contains V3x like this, and similarly V1y contains V2y contains V3y like this. These are the local bases at x and y respectively. Then clearly Vnx intersection Vn of y is not empty for every n belongs to n, because here open set intersects every open set containing x intersects every open set containing y. So here we observe that Vn of x intersection Vn of y is always non-empty. And so there is some point. So there is some xn in x such that xn belongs to Vnx intersection Vn of y for every n belongs to n. So we get the sequence xn such that xn belongs to Vn of x and xn belongs to Vn of y for every n. Actually there is some element in the intersection and we are assuming or we are actually denoting these elements as x1, x2, x3 like this, and so we get a sequence with this condition. As G, suppose G and H be arbitrary open sets such that x belongs to G and y belongs to H. As B of x is the local base at x, so there exists some member of the local base, and suppose that member is B naught x. B naught x is contained in B naught x contained in G, and so we get P in x is contained in G for every n greater than or equal to n naught. Why we have this condition? Because we have a monotonically decreasing sequence of sets. So Bn naught of x contains Bn naught plus 1 of x, and so we can say that Bnx is contained in G for every n greater than or equal to n naught. And so since xn belongs to Bn of x, so xn belongs to G for every n greater than or equal to n naught. And what we get here? G is any open set containing x, and we find that xn belongs to G for every n greater than or equal to n naught. Means every open set containing G contains infinitely many terms of the sequence, and so we can say that sequence xn converges to x. And similarly, for y we can consider that there exists some m naught in n such that Bm naught y is contained in H, and so Bn of y is contained in H for every n greater than or equal to n naught. Here we are using the same condition because we have monotonically decreasing sequence of sets. So Bn naught of y contains Bn of y for every n greater than or equal to n naught, and so Bn of y contained in H for every n greater than or equal to n naught, and so this implies that xn belongs to H for every n greater than or equal to n naught. Here note this, xn belongs to Bn of y. So xn belongs to H for every n greater than or equal to n naught, and so here we can say that every open set containing y contains infinitely many terms of the sequence, and so the sequence xn converges to y. So here we get a contradiction, that is sequence xn converges to x and y 2 points, which is a contradiction, and so our assumption is wrong, that is our space is